So up to this point, we have followed a fairly specific process to find Taylor series of functions. We started our process by calculating the various derivatives for our function, and then we plugged our a value, our value of the center, into those derivatives. And then we took those values that were output by the derivatives and we used the Taylor polynomial formula to get the function's Taylor polynomial of some degree. Then, by looking at the terms in the Taylor polynomial, and by looking at the pattern formed by those terms, and by extending that pattern using pattern recognition, we were able to extend the finite Taylor polynomial into an infinite Taylor series for the function. However, as you guys have been working on some of the questions that you've already encountered in class, you've begun to see that there are a couple of drawbacks to this particular pipeline that make it hard to use this process in certain situations. For example, if you're working with a function that has complicated derivatives, for example, a function like cosine of x squared, where you have to use chain rule and eventually product rule to find the higher order derivatives of the function, calculating the derivatives can become a real pain after a while once you start to get to the second and the third and the fourth derivative of the function. So this is the sort of first weakness of this process, which is that what if you're working with a function whose derivatives are hard to calculate? The second weakness that a couple of students already have begun to foresee is that if your function is of a sufficiently complex nature, it may be difficult to see and understand the pattern that's showing up in the terms of the Taylor polynomial, which might make it different to then extend that pattern of terms or to convey that pattern in your Taylor series formula. And these are absolutely correct as concerns. And this pipeline, to tell you the truth, is really only suitable for functions of a fairly simple nature. Functions that have fairly simple derivatives, functions that have fairly simple Taylor polynomials, which in turn give rise to fairly simple Taylor series. When you're dealing with more complicated functions, we're going today to introduce an alternative process for finding their Taylor series and their Taylor polynomials. And what we're going to do is we are going to take these simple Taylor series for like the exponential function sine cosine 1 over 1 minus x. We're going to take those simple Taylor series for simple functions and we are going to combine and manipulate them in a couple of different ways to allow us to obtain Taylor series for more complicated functions. Then, having those Taylor series for more complicated functions, we can always proceed to find more complicated Taylor polynomials simply by taking the infinite Taylor series and stopping the series and truncating it at whatever point or degree we may need for our application. And then, as you saw in problem set number 2, you can even go further than that, walking through this process backward, and you can use these Taylor polynomials as a way to find relatively complicated derivatives easily as well. By just comparing the coefficient that appears in the Taylor polynomial formula with the coefficient that appears in the Taylor polynomial that you have already calculated. So that's the topic of today's video. We are going to be learning how to take simple Taylor series and construct more complicated Taylor series from those, and that will allow us to get more complicated Taylor polynomials and more complicated derivatives in situations where we might need that. So to give you an example of this process, let's begin by working with the function f of x equals that cosine of x squared. Once again, this is a situation where I would not want to use this original pipeline to find the Taylor series for this function, because maybe the first derivative of cosine of x squared is easy enough to calculate, but once you start to get to the second derivative, which is going to require a product rule, and once you get to the third derivative and maybe the fourth derivative, things are going to get much more time consuming and labor intensive to calculate. So instead, I'm going to use this process of recycling or maybe upcycling these older Taylor series, these simpler Taylor series that we found in the previous video. For example, maybe I will start out by reminding myself of the Taylor series for just cosine of x, which we found previously. Let's recall that cosine of x was exactly equal to the series as the index goes from k equals 0 up to infinity of minus 1 to the power k times x to the power 2k divided by 2k factorial. Now, whenever we're working with an equation, we remember from all the way back in algebra that there's this principle with equations of whatever happens on the equation's left side, we need to do exactly the same thing. Exactly the same thing must happen on the equation's right side. What happens on the left also happens on the right. So if I take my cosine of x, and instead, I look at cosine of x squared, as I have in my problem. This action on the left-hand side that has transformed cos x into cosine x squared is a replacement, a substitution, replace x by x squared. Having taken that same action on the left-hand side, I need in this equation to take exactly the same action on the right-hand side. So make that swap in the function means make that swap in the series. What was previously x to the power 2k, I'm now going to replace that x by the quantity x squared and raise that to the power 2k. So this action on the left, I've done the same action on the right. And just by making that substitution, I have achieved the Taylor series for cosine of x squared. The Taylor series for cosine of x squared is equal to this series k goes from 0 to infinity of negative 1 to the k, x squared raised to the power 2k, divided by 2k factorial. You can leave it in this format, but it might be more useful for us to go ahead and use the exponent properties to simplify that. And we get x to the 4 times k in that exponent after simplification. So this would be my final answer to this question. Find the Taylor series centered at 0 of the function f of x, which is equal to cosine of x squared. I started with a simple Taylor series that was similar in shape to the function I was working with. I identified the action that took that simple function and turned it into my more complicated function. Here, that action is substitution. And then I performed exactly the same action in the series on the right-hand side. In this case, that exact same substitution. So for this function cosine of x squared, we find ourselves in a situation where we have the Taylor series before we have anything else. So from this Taylor series, we can now calculate the Taylor polynomial. From that Taylor polynomial, we can now calculate its derivatives, and let's get a little bit of practice doing that. Part B, find the Taylor polynomial of degree 8 of this function f of x equals cosine of x squared. So once again, I emphasize what you do not want to do in this situation is try to find, God forbid, 8 derivatives of cosine of x squared. That's going to be very time consuming, very labor intensive, and you're going to be very likely to make a mistake somewhere along the line. Instead, I'm going to remind myself that in part A, I already found the Taylor series. And from the Taylor series, I can find any Taylor polynomial of any degree very easily just by writing out the terms of the series until I hit the degree that they are asking for. And then I can stop writing terms. So for example, in this case, taking the Taylor series for cosine of x squared, I will begin by writing out the very first term in the series, which corresponds to an index of k equals 0. So if I take 0 and put it into this slot, and this exponent above x, and this factorial in the denominator, I get minus 1 to the power 0 is 1, x to the power 0 is 1, and 0 factorial in the denominator is also 1. So all in total, after simplification, that very first term corresponding to a k equals 0 is 1 unit. So now I increment the counter. K value is now 1 unit instead of 0. And I plug k equals 1 into this formula. So I get negative 1 to the power 1. And that's multiplied by x to the power 4. And that's divided by 2 factorial. So here we have negative x to the power 4 divided by 2 factorial. Okay, we still don't have a high enough exponent on the x. We need an exponent of at least 8 in order to be able to stop. So let's go ahead and increment k one more time. And we plug k equals 2 into this formula, and we get negative 1 squared. So that's positive. We get x to the power 8 from 2 times 4. And we get 4 factorial from 2 times 2 factorial. So writing that down, plus x 8 over 4 factorial. And now that we have an exponent of 8 on our x, we have achieved the polynomial of degree 8, centered at 0, for this function, just by writing out terms of the Taylor series until we had enough terms for our purposes here. Now, let's continue exploring what it looks like to go sort of backwards through this pipeline. And now that we have this more complicated Taylor polynomial, let's go ahead and use that to find some more complicated derivatives. So someone says, okay, what is the 7th derivative of this cosine function with 0 plugged in? Once again, I emphasize you do not want to be calculating 7 derivatives of this function by hand. It's just going to take too much time. So instead, what I'm going to do is I'm going to remember the role played by this derivative in my Taylor polynomial formula. The Taylor polynomial formula for a center of a equals 0 has the term where we have x minus 0 to the 7th power divided by 7 factorial times the 7th derivative of the function with 0 plugged in. So the Taylor polynomial formula says that your polynomial is going to have this term inside of it. This is going to be the format of your 7th exponent term. Now, meanwhile, if I look at the Taylor polynomial that I calculated indirectly back in part B, I can also see that the x to the 7th term has vanished here, right? The x to the 7th term must have a coefficient of 0 because it has vanished and it's not visible in our Taylor polynomial. So let's note that as well. Meanwhile, my Taylor polynomial from part B has a vanished x to the 7 term. So because of that, it must be true that the coefficient of x to the 7 in the Taylor polynomial must be the same as 0, because that 0 attached to the x7 would be what would cause that term to vanish in the Taylor polynomial that I have calculated. And so from that, we can deduce that the 7th derivative of cosine of x squared becomes 0 when you plug 0 into that function. Correspondingly, if I asked for the 8th derivative of cosine of x squared with x equals 0 as the input, I could get data about that 8th derivative by looking at what's happening at the x to the power 8 term in my Taylor polynomial. The Taylor polynomial formula from the first day of class says that the coefficient of x8 should be the 8th derivative evaluated at 0 divided by 8 factorial. But if I compare that to the Taylor polynomial that's standing directly in front of me, I can see that the coefficient of x to the 8 is visibly equal to 1 over 4 factorial. So just by comparing those two, you can deduce from that the value that x to the 8th must be equal to. Rather, I should say the 8th derivative of f, what that value must be equal to. These two are the same coefficient, so they must have exactly the same value. In other words, they have to be equal to each other. So this coefficient must equal this coefficient, and as a result, we can deduce that the value of the 8th derivative must have been 8 factorial over 4 factorial. So this is a demonstration of how higher order derivatives can be calculated very quickly for certain functions by reading the coefficients in their Taylor series. So to summarize, before we go to a few more example problems, the process is, we have this library of simple Taylor series that we found for e to the x, cosine of x, sine of x, and 1 over 1 minus x. We found those simple Taylor series following this process, finding the derivatives first, then finding the Taylor polynomial, then extending that into the Taylor series. However, for more complicated functions whose derivatives are harder to calculate or which are harder to understand, it's usually more practical to create the Taylor series for a complicated function by recycling and manipulating the Taylor series for a simpler function. And then if you need the Taylor polynomial, you can just truncate the series. If you need the derivatives, you can just look at the coefficients of the series. Alrighty, to finish off this video, let me just go ahead and demonstrate a couple of different manipulations and combinations that can give rise to Taylor series of more complicated functions. For example, if I said to you, I want the Taylor series centered at 0 of the function 1 over 1 plus x. The very first thing that I'm going to do is acknowledge how similar this function is to the function that I saw in yesterday's video, which was 1 over 1 minus x, and which we saw had the series representation, the sum of just x to the power k. Now, my function is very, very similar to that one, except instead of having a subtracted x, it has a positive x. Or, put another way, my function is equivalent to x minus negative x in that denominator. The reason why I've rewritten my function in this format is because now I can more easily identify the action that has turned this original simpler function into my slightly more complicated function. The action that is happening on the left is that x has been replaced by minus x. So if I want to find the Taylor series, all I have to do is take exactly the same action on the right-hand side. In my series, instead of raising x to the power k, I'll simply raise the quantity negative x to the power k. You can leave it in this format, or if you prefer, you can reformat this series slightly, and you can write it as the sum as k goes from 0 to infinity of split off that minus 1 to the power k separate from x to the power k. This is an alternative way to write it if you prefer, and this is nice in some ways. It makes it easier to see that the series is going to alternate in sign back and forth from plus and minus. So here's my final answer to this part A question, the Taylor series of 1 over 1 plus x centered at 0. Part B, find the Taylor series centered at 0 of the function 1 over 1 plus x squared. So let's see if we can find this Taylor series by recycling one that we have already found. For example, we found just in part A, just a moment ago, that 1 over 1 plus x was this alternating the sum as k goes from 0 to infinity, minus 1 to the k, x to the power k. And so if we compare our part B function with the one that we were working with in part A, if I were to articulate the action that has transformed this function into this function, I could say that the action is that x has been replaced by x squared. So all I need to do is take exactly the same action on the right-hand side. And instead of x to the k, I now have the quantity x squared raised to the power k, which, once again, optionally can be simplified. If you want to, you can turn this into the sum as k goes from 0 to infinity of negative 1 to the power k, x to the power 2k, using the exponent properties to compress this exponent expression. Answer box. Alrighty. Now, part C asks, find the Taylor series centered at 0 of the function arctan of x. Now, in this situation, it may not be quite so obvious the relationship between arctan of x and some of the other functions that we've worked with throughout this problem. But you may remember from either Calculus 1 or Calculus 2 that there is a derivative antiderivative relationship between 1 over 1 plus x squared and arctan. So if I start with the function that I just found in part B, 1 plus x squared, being equal to the series, the sum of minus 1 to the k, x to the 2k. And I think about the action that turns that function into arctan. The action is to take an antiderivative on the left. So all I have to do is take exactly the same action on the series on the right. Fortunately, because of things like the sum rule, because of things like the constant multiple rule, because of things like the power rule, finding the antiderivative of this series on the right side is actually not that bad, because really you can just take the antiderivative of each of these terms separately using the power rule, because each of these terms is a power function, x to some power. So if I apply the power rule on the right-hand side to find the antiderivative, I get the sum as k goes from 0 to infinity of negative 1 to the power k. And then I'm using the power rule for integrals, so I will increase the power by 1 unit, and then I will divide by that increased power. X to the power 2k plus 1, and then divided by 2k plus 1. So here we have the Taylor series representation of arctan of x, the inverse tangent function. You can continue this process. For example, if somebody says, what's the Taylor series centered at 0 of the function arctan of 3x? Once again, the action here is simply that the x and the 3x have gotten swapped. And if that's the action that was performed on the function, then you just have to perform the same action on the series. So we have arctan of 3x being equal to the sum, as k goes from 0 to infinity, of negative 1 to the k, quantity 3x to 2k plus 1 divided by 2k plus 1. And then further, if somebody asked me for a Taylor polynomial of that arctan function of degree, for example, 5, all I would have to do is take that Taylor series for that same function and truncate it and write out terms until I hit an exponent of 5 and then stop. So for example, starting out in that Taylor series with a k value of 0, if I plug k equals 0 into this expression, I get minus 1 to the 0 times 3x to the power 1 divided by 1. After cleaning that up, that's just 3x. If I increase the index one more time and let k be equal to 1, that minus 1 to the power k is returning a negative value. Now my exponent is 2 times 1 plus 1, so I'm getting an exponent now of 3. And likewise, in the denominator, I have 3. So in this term, I can see the exponent that will be on x is 3, and that's not high enough for a polynomial of degree 5. So let's keep going. If I increment k one more time and bring it up to 2, and I plug 2 into this series formula, I get plus now from the -1 to the k, and this exponent 2k plus 1 becomes 5 from 2 times 2 plus 1. So just by truncating this Taylor series, we were able to find the Taylor polynomial of degree 5 for this function. And we did not have to calculate 5 derivatives of arctan of 3x, heaven forbid. We just had to recycle some other series that we were able to find more easily through this succession of substitutions and antiderivatives and things like that. So that's today's lecture, talking about upcycling or recycling of Taylor series, finding Taylor series of complicated functions by manipulating Taylor series of simpler functions.